All right, we're still in Unit 2. We're on Section 3 on triangles and triangle segments. This includes altitudes, mid-segments, and bisectors. So to begin, we're going to review some of our classifications, go over a few terms, and in our second video, we'll go over some examples. So again, just to review, scalene triangles are triangles that have no equal sides and no equal angles. Okay, again, it's kind of an implication. If all of the sides like in this triangle, we can see we did 1 tick mark here, 2 on this one, and 3 there. That's saying each of those is a different length from each other. That's going to imply then, because they're all different, that this angle, and this angle all have to be different measures. Okay? You can't have the same angle but different lengths as your triangle sides. Okay? So it has to have 3 different angles, 3 different sides. That would be a scalene triangle. An isosceles triangle is a triangle that's going to have exactly 2 equal sides and 2 equal angles. No more, no less. And again, that's kind of an implication. This one, we had our 2 tick marks here and 2 over here. That means that this length and this length here are the same. That also means then, if we look at this length, go right across from it to this angle, okay, so the one right across from it has to be equal to the angle across from the other one. These ones are right across from each other, so these two lengths, this one here and this one here, are equal. Now, we don't necessarily know exactly what measure they are, but we know they're equal. Same thing, these two angles, this here, this one here, we don't know exactly what they are, but whatever they are, they have to be equal to each other. It's kind of an implication of isosceles triangles. An equilateral triangle, or you can call it equiangular. The equa in either case, equa here, oops, that's above, below equa, that means equal, they are the same. Lateral means sides, so same sides. Equiangular, that means all the angles are going to be equal to each other. So equiangular triangle means it has all of the same angles. Equilateral has all the same sides. They mean the same thing. If a triangle has all the same angles, that implies that they're all going to be 60. That would be an equiangular triangle. It can't be equiangular without being equilateral. So this triangle here kind of shows that all of the angles are the exact same. All of the sides are marked as the same. Now again, each triangle here is saying the same thing. Because on this one we have 2 tick marks, 2 and 2. The ones across from them, this angle, and this angle, they all have to be the same. So even though it wasn't marked like that, because you know it's an equilateral triangle, you can just imply that they are all going to be the same. Right triangles. Any triangle that has exactly 1 right angle would be called a right triangle. Now again, you can't have any more. You can't have 2 right angles. That would be too big of a figure. You can't have any less. If there's no right angles, it's no longer a right triangle. So this one has nothing to do with the sides. It's just saying based on there's 1 angle that is a right angle, 90 degrees, so we call it a right triangle. Okay, an implication of this is if it is a right triangle, it cannot be equilateral. By definition, it cannot be, because equilateral has all 60-degree angles. Right triangle has at least 1, or exactly 1, that is 90 degrees. So you can't have something that's a right triangle that is also equilateral. It will not work. Now, it can be isosceles, and you can kind of see this one looks kind of isosceles. There's no way to prove it, but we can see that those look about the same length. So you can have it be isosceles and right, that is possible, but it just cannot be equilateral. Now, one more thing to add on to right triangles. Whichever angle is your right angle, the side across from it is called the hypotenuse. The other 2 sides would be called the legs. Oops, that one went right through the leg there. Other times, we may label each of these legs as a letter. And most of the times, you'll see the hypotenuse be labeled as C, and the 2 legs, doesn't really matter which is which, we would label as A and B. And one of the reasons we do that is because it makes it real easy to write our Pythagorean theorem, which is a squared plus b squared equals c squared. Now, the Pythagorean theorem only works for right triangles. Okay, we can't use it to say the same about other triangles. But for the Pythagorean theorem, if a triangle is a right triangle, then the measure of one of the legs squared plus the measure of the other leg squared has to equal the measure of the hypotenuse squared. A squared plus b squared equals c squared. That's our Pythagorean theorem. Two more definitions that you might not have on yours. I want you to write these in. An acute triangle is a triangle with all angles that are acute. So if I draw something, let's see, like that, something close to that. That was kind of a goofy, kind of an off drawing. But if we can tell that all of these angles are less than 90 degrees, then that would be an acute triangle. All of them have to be less than 90 degrees. All of them are acute. An obtuse triangle, a little easier to draw. You just need at least one obtuse angle. This one here. We can tell that's obviously bigger than a right angle. And then the other angles, just kind of connected anywhere. As long as there's at least one obtuse angle. In fact, there can't be any more than one. There has to be just one obtuse angle. Then it is called an obtuse triangle. So for measuring or judging our triangles based off of their angles, we can have acute triangles, we can have obtuse triangles, or we can have right triangles. Those are the only ones we can have. So if we wanted to classify each one specifically, again, each time that you name a triangle, you need to name it by the sides and by the angles. So if we look at this first one, we can see that each one of these measures is different. So that's how we got scalene. Now again, it's kind of hard to tell. We don't have any measuring devices. So in this one, we're going to kind of guesstimate. This angle, they all are going to be different. And this angle, they all look less than 90 degrees. So again, this is kind of more of a guesstimation, but we'll say that they're each acute. So this would be called a scalene acute triangle. You have to put both terms on there to describe it. Okay, let's look at number 2, one below it. Again, we have 3 sides that are exactly the same, so that would be called an equilateral. They are all the same. Equilateral also implies that it's acute, because again, each of these angles is going to be 60 degrees. So they're all, for sure, less than 90 degrees. So it would be an equilateral acute triangle, or you could also call it equilateral equiangular, because we know they're all exactly 60. Let's look at number 3. We have these 2 segments that are going to be equal to each other. They're congruent segments on the sides there. Because we have 2 sides that are equal to each other, it is called isosceles. And because we have a right angle in this corner here, it is an isosceles right triangle. So again, you have to describe it as specifically as you can. So you use the sides and the angles to show what it is. This last one got cut off just a little bit. Let me extend this page. There we go. Again, we can see that each of these sides is a different length because they all have a different amount of the tick marks on them. So no sides are equal to each other. That's called scalene. And this angle here looks a little bit bigger than 90. So again, it's a guesstimate. We don't have protractors to measure it, but it looks like it's a little bit bigger than 90, so we're going to call it obtuse. This would be a scalene obtuse triangle. And that'll be it for our definitions.